Hello everyone, this is Lavanya. I'm working as Senior Application Engineer in Low Frequency Electromechanical team. Today I'm going to give a presentation on shape optimization for laminations using Flux. These are the contents of the presentation. First, I'm going to give a brief introduction on shape optimization and then how to set up a shape optimization using Altair Flux, and then this shape optimization will be implemented on Reluctance machine. And then I'm going to conclude with a comparison of results for different types of optimizations. There are three basic types of optimizations: size optimization, shape optimization, and topology optimization. So in size optimization, the geometric dimensions are changed to obtain the optimum design. Here in this case, the thickness of the boxes are varied to obtain an optimum design. The second one is a shape optimization, wherein the borders of the faces are given as an input to obtain an optimum shape to get the required responses. And the third one is a topology optimization, where you start with no geometry, just the global borders, and then at the end of the optimization, you're going to see the faces of the design. Today, we're going to look at shape optimization in Altair Flux. Before we start with the shape optimization, you need to install OptiStruct and compose at least a version of 2021.1, and it could be a higher version also. This will be available for download in Altair One Marketplace. Then after downloading, you should configure the path for the compose and the OptiStruct in the options under supervisor of Flux. Then moving on to the shape optimization. Here, the shape optimization feature can be found under solver. Under optimization window, you will be able to see different options for the setup of shape optimization. At the latest in version 2022, this shape optimization is possible for magnetostatic and transient magnetic applications. And this shape optimization can be implemented for the faces which have both linear or the non-linear material. Parametric study is also possible without a remeshing. And the faces of the magnets can also be included for shape optimization, but the orientation of the magnetization cannot be changed. Under responses, we have several options to give as an input. Those are the flux through the coils, flux through faces or lines, torque on a path, and the magnetic forces on a path or on the lines that you select, and also the input response can also be the volume of the faces, where you can optimize it to reduce the weight of the machine or keep the weight of the machine to your target. And then the constraints that are allowed to be assigned are the volume of the part or face or a device, or the symmetries can be given as a constraint. And the second one is all the responses that you have defined for the optimization can be used as the constraints also. And the fourth one is the feature of using compose function, wherein you can define any complex function to be considered as a constraint, and that can be used to define your limits for optimization. Moving on to the responses that you can define using shape optimization. They are flux flowing through the faces, lines, and the force that the magnetic force can be computed on the path that is defined. And the third and fourth one is sum of the fluxes on the selected coils. This you can do it as a sum of the different coils that you have on the model, or you can also define a single coil. And the fifth one is torque can also be computed on a path that is defined, and this torque can be used as a response or the constraint for your optimization. And the last one is the volume of the 2D faces. As I have mentioned in the previous slide, you can use this as an input to keep the volume as a response, which is nothing but as an objective, or you can also use it as a constraint to restrict the volume of the faces, or to restrict the weight of the machine or on which you're working on. And next, moving on to the constraints, you can define any type of constraint, as I have mentioned in the initial slide, like the symmetry constraint, volume of the faces, and then the responses that you defined in the previous one. And then also you can define the constraints with the using the compose function. Here, these are the two constraints which we are going to use to our today's application. Sorry, an example. Here, the first one is the constraint with the symmetry, where you're going to define a symmetry constraint. Then when you do a shape optimization, the way the mesh elements changes will be same as how you see on the opposite side. And the next one is the constraint on the volume, where you select the volume of the rotor lamination, and then you're going to bound it to a particular bounds. This is actually to put it below 80% of the volume of the face. This is how you define an optimization problem, which is nothing but the objective. So you can give the maximize or the minimization of the function, and then define if it is a predefined function, which are nothing but the functions that are already available, like the flux to the faces or lines, or the flux through the coils, or the torque, magnetic force, or the volume. And then you can define your responses and constraints in here, or you can define it as a compose function, and also you can choose your responses and constraints in here. So for the design responses, you can, for all the responses, either you can choose the design responses that are already defined under responses, and the other facilities we have is for the compose function. And then the last option is to define the optimization options. The first one is the tolerance, wherein you define the minimum variation that can be allowed and the optimization can stop if the variation is below 0.5 in this case, or the value you define. And the maximum number of iterations. So once the optimization reaches to this defined maximum number of iterations, and the optimization stops. And then using the moving limits and the sensibilities filter, you're going to define the area in which the nodes are going to move. If you leave it as automatic, the algorithm going to choose what is the relative factor that is there, and then it's going to change the mesh nodes in that area limit, or you can also define your specified area limits in here. And then moving on to the tolerance. Tolerance is used to control how close the lines of the final design can be. For example, if you have 0.5, that means half of the meshing size. And then the final one is you can choose if you want to open the final optimized design or not. This shows how you can define a compose function. Here under optimization problem, if you choose a compose function option, then you'll be able to import the compose function which you define. So the figure in here shows the example of a motor torque that is being computed using Park's equation using the compose function template. Here we have an objective function with the inputs of the responses that we give as an input, and other responses also. And those as an input, here, for example, the inputs are the flux of the coils. So the flux of the coils are used to compute the torque of the machine. The current, the three-phase currents are also obtained using the control angle, peak current value, and the angular position variation from 2 to 180 degrees of angular position. So this is how you can get your compose function and use it for the shape optimization. For the optimization of synchronous reluctance machine, we are going to input rotor air gap interface and the rotor holes or the windows as an option for shape optimization. And then the goal is to maximize the torque. And here torque is computed using the Park's equation. For this equation, the inputs will be three-phase currents and the flux in the three-phase coils. And this function is computed using compose function. And 4 different optimizations will be carried out for this machine. First one is the basic optimization without any constraints. The second one is the optimization to improve torque with symmetry imposed. And the third one is with a constraint on rotor mass reduction. And the fourth one is the optimization with a constraint of symmetry and rotor mass reduction on the machine. Now let's look at how to set up shape optimization for synchronous reluctance machine. So you need to open Flux before start. So go into search or Windows and click on the Flux 2022 or the version you have, and then Flux Supervisor will open. In the window, go into Options and under Couple Software, check if the paths for the compose and OptiStruct are defined correctly or not. If they are not defined, click on this icon and then you'll be able to select the path of the file that is that has been installed. And once they are defined, click OK. Now open the project of the model on which you wanted to apply shape optimization. So this is a model for me, and now I'm launching it. The model is starting to open. Now for this model, we have all the setup done, like the geometry, mesh, physics, circuit, etc. Scenario has also been defined. Now under solver, we'll see an option called optimization. In that, we have to start defining our responses, constraints, and the optimization problem. Now, the first one is responses. Let's start defining it. So under responses, right click on it, and then we can create a new response. This is coil flux, which will be used as an input for the optimization. So this here, I'm selecting some of the flux of selected coils, but we need only flux for one coil. So I'm selecting one and then click OK. So now a response will be created. And here you'll be able to see that. And now for the constraint, right click on the constraint, click on the new. I'm giving the volume constraint first. So for the volume constraint, we are going to select 2D faces, and then I'm going to select our rotor lamination face. But here, and then we have to set the boundaries for the volumes. So this I'm giving it as 1e minus 5 as lower bound, and this one is 5.3305 e minus 5 as upper bound. This is nothing but, this value is nothing but the 80% of the current rotor volume. So the goal is to reduce the volume of the rotor lamination at least by 20%. Now after defining this, click OK. After that, we are going to define a symmetry constraint. And we are going to select the optimum constraint as symmetry constraint, and then give its origin and give the direction of axis. I'm going to select 1, 1, and then it's going to be here. The symmetry axis is going to be here once we define it this way, and then click OK. Now the symmetry constraint is done. And then now we are going to give optimization problem. Since we have defined both the constraints of symmetry and volume, And then for the new optimization problem, right click on optimization problem and click on new. Now here, let me define it as no constraints. Okay. Under no constraints problem, we're going to select maximize, click on optimization compose function. Now here we'll be able to select which function we want. So we are going to select the objective function, click open, that will be selected, give its name, I'm leaving it as I want. And then for the response, I'm giving coil flux as an input. Now click OK. An optimization problem will be created. Here, what is the compose function? So here, when I selected the compose function, this is the function that is being given as an input. This function is used as an optimization problem in here. And now this we have first one we have set up a no constraint problem. Now we are going to give a constraint problem. This is with volume constraint. So in here we are going to leave the response as same, but in the constraint we are going to include a volume constraint and then click OK. And another one we are going to create a symmetry constraint. So here we're going to leave everything else as same, but here we are going to replace a volume with the symmetry constraint. So that is one optimization problem. And now when you want to give two constraints, then in addition to the symmetry constraint in here, we are going to add volume constraint also. And then click OK. So we have completed defining the responses, constraints, the symmetry and the volume, and the no constraints. Sorry, all the optimization problems that we are going to do on a reluctance machine. So once you set up all these, now we can run the shape optimization. So to run it, so we need to go into solving, click on run shape optimization. Here we have a scenario that already been defined. So let's select that, and then under working directory, you can select the folder in which you want it to save. So you can create a new folder and give it as SRM no constraint, and then select that folder to save all the results, log files, and the movies and the optimization function, trends, everything in this folder. Now select the optimization problem. I'm selecting the no constraint, and then we need to select the lines for optimization. That we can do it easily by going into this arrow and then select by face, and now I'm selecting the lamination. Okay. But for shape optimization, we cannot have the borders as the lines for optimization. So I press on Control and select the unwanted lines. Okay. Now we have all the lines that we wanted to put for optimization. Now click on OK. Now once you start the optimization, the physics check will be done and then optimization starts. So when the optimization starts, you will see a command window popping up and runs each iteration, and you'll be able to see all the steps that will run for a scenario. So here is a window that popped up, and then it's running the 2D application. Now, after the optimization is completed, you will see on the output window an information as in the picture below. The information consists of the number of iterations that are being used to come to an optimum solution, and then what's the initial value and the final value of the objective function, and what's the change from the initial to the final value. And then You'll also see the information of where all the results have been saved, and then the movies, which shows how the shape has been changed over the iterations, and then how much computation time has been required to come to a solution. And then you will be seeing an Flux file opening after the optimization is completed, and this is the optimized model after the shape optimization without any constraints. And you can see how the shape of the windows in the rotor lamination has been changed to improve the torque of the reluctance machine. And then after that, this is how you'll be able to see the movies, wherein this is one of the movie with the volume for the shape optimization, and you'll be able to see how the shape is being changed. So this kind of movie will be automatically saved in the folder that will be that is given in your output window. And then similar optimization is performed for all four of them. So first one is for the basic optimization. This is how you see the windows and the outer diameter of the rotor changes for the basic optimization without any constraints. When symmetry is imposed as a constraint, then you'll see that the holes or the windows in the rotor lamination will be changed similarly on both the sides, on this side and on the other side, in the same way, which is not the same in the basic optimization. And then the third one is with the rotor mass constraint. The windows has been reduced more to bring down the rotor mass volume to at least by 20%, and this is how the rotor shape looks like with the rotor mass restriction. And then with the implementation of both rotor mass and the symmetry imposition, then you'll see that the windows are equally optimized on both the bottom and the top sides. And then and also you'll see a rotor mass reduction. As a comparison, you will see we can see that the rotor mass is 2.4 kgs and the mean torque is 11.87 for an initial design. And then with all the different design constraints and objectives, there is a mass improvement of 2.17% under no constraint optimization, because there is no restriction put for the volume. But when in the symmetry imposed, there is much lesser difference in the mass improvement. But for the design 3 and 4, where there is a restriction for constraint for mass reduction, there is 20% reduction in the mass. And then looking at the computation time, without any restrictions, the shape optimization took 53 minutes to run the simulation. And then for design 2, it took 58 minutes where symmetry is imposed. And the third one is when the mass reduction constraint is imposed, the shape optimization took 79 minutes and 46 seconds. And then with both mass restriction and symmetry imposed, it took the similar time as the previous one, just a second's difference. It took about 79 minutes to give us an optimum design. And then looking at the torque improvement, when there is no restriction of the volume or symmetry, we were able to see a 15.66% of improvement in the torque. Whereas when the symmetry is imposed, which is the improvement is 15.22, which is not much different from the no restriction. Whereas with the mass reduction restriction, we are only seeing 13.71% of improvement. And with both mass reduction and the symmetry, we are seeing 12.75% of improvement in the torque. And coming to the conclusion, so shape optimization helps us in giving a significant improvement from the initial design with higher amount of performances from the machine. And this shape optimization is completely flexible. If you can use both the predefined functions and also compose functions. With the predefined functions, you can directly use the quantities that are being computed by Flux. But if you wanted to do a complex function, you can use those quantities which are computed by Flux as an inputs, and then build a compose function to define your goal functions or the constraints. And overall, shape optimization is a fast, robust, and efficient tool to do the shape optimization. And this concludes my presentation. Please let me know if you have any questions on the shape optimization.